We all know the story. An asteroid, a 6-mile wide rock from space, slammed into the Earth. It created a crater the size of a small country. The impact threw so much dust and debris into the air that it blocked out the sun. The world went dark and cold. Plants died. Then the herbivores that ate them died. Then the carnivores that ate them died, and just like that, the dinosaurs were gone. It's a good story. It's dramatic. It's simple. And for the most part, it's true. The Chicxulub crater is there, buried under the Yucatan Peninsula in Mexico. The layer of iridium, an element rare on Earth but common in asteroids, is found in rocks all over the world, dating to precisely that time, 66 million years ago. The evidence is solid, case closed. But what if it's not the whole story? What if the asteroid was just the final blow in a fight that dinosaurs were already losing? What if the real killer was something else? Something that came not from the sky, but from deep within the Earth itself? And what if that same killer has been at work at other times, responsible for extinctions far worse than the one that wiped out the T-Rex? The other suspect is a volcano, but not the kind of volcano you're picturing. Not a single neat cone like Mount Fuji or Mount St. Helens. This was something else entirely. A different scale of disaster. Imagine a crack in the Earth's crust that stretches for hundreds of miles. And from that crack, for thousands and thousands of years, lava pours out, not in a single explosive eruption, but in a relentless, massive flood. This type of event is called a Large Igneous Province, or a LIP. The lava flows and spreads, covering vast areas of land, sometimes the size of a continent, in a thick blanket of black volcanic rock. The one that was active at the end of the age of dinosaurs is called the Deccan Traps. You can see the remains of them today in India. They cover an area of 200,000 square miles, and in some places the layers of old lava are more than a mile thick. And here's the crucial part. The main eruptions of the Deccan Traps happened right around 66 million years ago. They started before the asteroid hit and continued for some time after. The timing is almost perfect. Too perfect to be a coincidence. So, we have two suspects at the scene of the crime. The asteroid from above and the volcano from below. For a long time, scientists argued over which one was the true culprit. Team Asteroid pointed to the suddenness of the iridium layer. It looks like a single, catastrophic event. Team Volcano pointed to the sheer scale of the Deccan Traps and the long-term environmental damage they must have caused. The lava itself isn't the main problem. A lava flow is a local disaster. It buries whatever is in its path. But the Deccan Traps were in India. How could they kill a Triceratops in North America? The real weapons of a LIP are the gases. These eruptions release unimaginable amounts of gas into the atmosphere. The big one is carbon dioxide. CO2 is a greenhouse gas. It traps heat. Over thousands of years, the Deccan Traps pumped so much CO2 into the air that the global climate began to warm up. The planet got hotter. Weather patterns changed. Ecosystems were stressed. Then there's sulfur dioxide. When this gas hits the upper atmosphere, it can form tiny particles called aerosols that reflect sunlight back into space. This has a cooling effect, so you get this wild swing, a long, slow warming from the CO2, punctuated by sharp, sudden cooling events from the sulfur. These jolts to the climate are incredibly hard for life to adapt to. One year is hot, the next is cold. It creates chaos. The sulfur also leads to acid rain. When it mixes with water in the clouds, it forms sulfuric acid. The rain that is as acidic as lemon juice falls from the sky. It burns plants, it changes the chemistry of the soil. It makes the surface of the ocean more acidic, which is devastating for creatures that build shells like plankton and clams. And since plankton are at the very bottom of the ocean food chain, their collapse means the whole system starts to fall apart. So imagine you're a dinosaur living in that world. The climate is getting weird. The plants you eat are struggling with acid rain and temperature swings. The oceans are getting sick. Life is already hard. The whole planet is a patient with a high fever. And then a 6-mile wide asteroid hits. This is the picture many scientists have settled on now. It wasn't one or the other. It was a 1-2 punch. The world's ecosystems were already profoundly sick because of the massive volcanic eruptions. They were weakened, fragile. The asteroid didn't hit a healthy, thriving planet. It hit a planet that was already on the brink. The impact was the knockout blow, the final, catastrophic shock that a stress system just couldn't handle. This makes the story more complex, but also more real. Disasters in the real world are rarely simple. They are often a cascade of failures, a perfect storm of bad events. The end of the dinosaurs was likely just that. A world poisoned from within, and then shattered from above. But the story of volcanoes and extinction doesn't end there. In fact, the dinosaur extinction isn't even the most dramatic example. To see the true destructive power of a LIP, we need to go back much further in time, to an event that makes the end of the dinosaurs look like a minor fender bender. We have to go back to the end of the Permian period, about 252 million years ago. This moment in time marks the single greatest catastrophe in the history of complex life on Earth. It's called the Permian-Triassic Extinction Event. Most people just call it the Great Dying. And it earned its name. The extinction that killed the dinosaurs wiped out about 75% of species on Earth. The Great Dying wiped out an estimated 96% of all marine species and 70% of terrestrial vertebrate species. It is the closest life has ever come to being completely erased. For decades, what caused it was a profound mystery. There was no clear evidence of a giant asteroid impact, no telltale iridium layer. Scientists looked for a killer, and for a long time they came up empty, but then they started looking at a different part of the world. In Siberia, you can find the Siberian Traps. It's another large igneous province, but one that dwarfs the Deccan Traps. The Siberian Traps cover an area of nearly 3 million square miles. That's almost the size of the entire continental United States. The volume of lava was enough to cover the entire Earth in a layer 20 feet deep. The eruptions went on for a very long time, maybe hundreds of thousands of years. And their peak activity lines up perfectly with the Great Dying. Here, there is no asteroid to share the blame. The volcano stands alone as the prime suspect, and the crime scene it left behind is horrifying. The mechanisms were the same as with the Deccan Traps, but amplified to an almost unimaginable degree. The eruption didn't just pour out over land, it also erupted through one of the largest coal basins on the planet. This was like throwing gasoline on a fire. The hot magma cooked the coal, releasing colossal amounts of carbon dioxide and methane, another potent greenhouse gas. The planet's thermostat was broken. Global temperatures soared. Some models suggest the average global temperature rose by 10 degrees Celsius or more. The tropics may have become lethally hot for most animals, with land temperatures reaching 140 degrees Fahrenheit and ocean surface temperatures hitting 104 degrees. The oceans suffered the most. As they warmed up, they started to lose their oxygen. This is a basic physical property of water. The warmer it gets, the less dissolved gas it can hold. Circulation patterns in the ocean shut down, and vast stretches of the deep ocean became anoxic, completely without oxygen. Then something even worse happened. With no oxygen, certain types of bacteria thrived. These bacteria don't breathe oxygen. They breathe sulfate, and their waste product is hydrogen sulfide, a highly toxic gas that smells like rotten eggs. This poisonous gas started to build up in the deep ocean. The oceans became stratified. A warm, acidic, low oxygen layer on top, and a deep, black, toxic layer below, full of hydrogen sulfide. As the deep water occasionally mixed with the surface, this poison would bubble up, killing everything it touched. Some scientists even think this toxic gas escaped into the atmosphere, poisoning land animals and destroying the ozone layer, which would have let in deadly UV radiation from the sun. The world of the late Permian became a nightmare. The land was a hot, arid desert plagued by acid rain. The oceans were a warm, stagnant, poisonous soup. It's no wonder life almost winked out entirely. It was a planet trying to kill everything on it, and the cause was the Earth itself. A massive, prolonged volcanic eruption that fundamentally broke the planet's climate and chemistry. It took millions of years for life to recover. The world that emerged after the Great Dying was completely different. The dominant land animals of the Permian, strange mammal, like reptiles, were mostly gone. The slate was wiped clean, and into that empty world a new group of reptiles began to rise. We know them as the dinosaurs. The Great Dying shows the full, terrifying potential of a LIP. But it's not the only other example. The history of life on Earth is punctuated by these massive volcanic events, and they frequently line up with mass extinctions. Go forward in time from the Great Dying to about 201 million years ago. This is the end of the Triassic period. The dinosaurs are doing well, but they are not yet the undisputed kings of the planet. There are other large reptiles competing with them, like giant crocodile like phytosaurs and armored adosaurs. Then, another mass extinction happens, the end Triassic extinction. It wiped out most of the dinosaurs' competitors on land and many creatures in the sea. And what do we find right at that time? Another LIP. This one is called the Central Atlantic Magmatic Province, or CAMP. It was a series of eruptions linked to the breakup of the supercontinent Pangaea as the Atlantic Ocean first began to open up. The lava flows from Camp are found today in North America, South America, Africa, and Europe. It was another giant volcanic event, another huge puff of CO2 and sulfur into the atmosphere. And another major extinction. It wasn't as bad as the Great Dying, but it was still a global crisis. And crucially, it seems to have cleared the way for the dinosaurs. With their main competitors gone, they were free to diversify and grow to enormous sizes. The volcanic event at the end of the Triassic didn't just cause an extinction. It set the stage for the next 150 million years of evolution. It created the age of dinosaurs. So we see a pattern. A massive volcanic event happens. The climate goes haywire. The oceans turn acidic and lose oxygen, and a huge number of species die out. It happened at the end of the Permian. It happened at the end of the Triassic. And it was a major contributing factor at the end of the Cretaceous when the dinosaurs died. There are 5 major mass extinctions in Earth's history, known as the Big Five. We've now linked volcanoes to 3 of them. What about the other 2? The evidence is more debated, but the links are still there. The late Devonian extinction, around 372 million years ago, was a long, drawn-out affair, not a single event. But its timing corresponds with large volcanic eruptions in Russia, the Veluwe traps. The oldest of the Big Five, the Endordovian extinction around 445 million years ago, has always been linked to a sudden intense ice age. It seems like the opposite of a volcanic extinction, which we usually associate with global warming. But some recent research suggests that a truly enormous and sustained LIP could, at first, cause global cooling. If the eruptions put out a massive amount of sulfur dioxide, the sun-blocking effect could be so strong that it overrides the warming from CO2, plunging the planet into a deep freeze. Once the sulfur falls out of the atmosphere after a few years, the CO2 is still there, and the planet could then flip violently into a hothouse state. This volcanic winter, followed by a hothouse summer, is another way a LIP could trigger an extinction. So it seems that wherever you look, whenever there's a mass extinction, you can often find a giant volcano holding a smoking gun. They are not always the sole murderer. Sometimes they have an accomplice, like an asteroid or a sudden shift in continental plates. But they are almost always at the scene of the crime. It's worth pausing to understand exactly why these volcanoes are so deadly. The key is the difference between the lava and the gas. The lava is impressive, but it's a local problem. It's the gases that go global. Let's break it down again. Carbon dioxide is the big one for long-term change. ALIP can release more CO2 in its lifetime than humans have released in all of modern history. This is the primary driver of global warming. A hotter planet means new climate zones, changing rainfall, and heat stress on plants and animals. It also means melting ice caps and rising sea levels. Sulfur dioxide is the agent of chaos. In the atmosphere, it creates sulfate aerosols. These tiny particles are great at reflecting sunlight. This leads to global cooling, or a volcanic winter. This effect is temporary, lasting only a few years. But a lip isn't a single eruption. It's thousands of eruptions over a vast period. This could mean decades or centuries of unpredictable cold snaps, killing off crops and starving animals. After the cooling comes the second punch from sulfur acid rain. This damages forests and, most importantly, acidifies the surface of the ocean. Ocean acidification is a silent killer. Many marine organisms, from tiny plankton to corals and shellfish, build their skeletons and shells out of calcium carbonate. As the ocean absorbs more CO2 from the atmosphere, it becomes more acidic. This makes it harder for these creatures to build their shells. Their shells can even start to dissolve. If you kill off the plankton at the base of the food web, the entire marine ecosystem is in danger of collapse. Ocean anoxia is the final piece. A warmer world leads to warmer oceans. Warmer water holds less oxygen. At the same time, the acid rain and land-based disruption can wash huge amounts of nutrients into the sea. This can cause massive blooms of algae. When this algae dies, it sinks and decomposes, a process that uses up even more oxygen. This creates huge dead zones where nothing that needs to breathe oxygen can survive. As we saw with the Great Dying, this can lead to the production of toxic hydrogen sulfide gas, turning the ocean into a poison reservoir. When you put all these things together, you have a recipe for global disaster. It's not one single problem. It's a cascade of interconnected environmental crises. The world gets hot, then cold, then hot again. The rain becomes acidic. The oceans can't breathe. The food webs on land and in the sea fall apart. This is a much grimmer and more complex picture than the simple story of an asteroid strike. It's a slow, grinding process of the planet's life support systems being systematically dismantled from within. This raises an obvious and slightly uncomfortable question. Could it happen again? Yes, large igneous provinces are a natural part of how the Earth works. They are linked to plumes of hot material rising from deep within the planet's mantle. There is no reason to think they have stopped happening. The last truly massive one was the Columbia River Basalt Group in the Pacific Northwest of the United States about 16 million years ago. It was big, but not on the scale of the Siberian or Deccan traps, and while it caused some environmental change, it didn't trigger a major mass extinction. Geologically, we seem to be in a quiet period, but the story of these ancient volcanoes carries a warning. And the warning is not about lava, it's about gas. It's about what happens when you rapidly dump huge quantities of carbon dioxide into the atmosphere. The ancient world provides a case study. The Earth's systems can be pushed past the tipping point. The climate and ocean chemistry can change dramatically and quickly, and when they do, life suffers on a massive scale. The LIPs that caused the great extinctions did this over thousands or hundreds of thousands of years. They were the fastest natural source of carbon emissions in Earth's history. Today, through the burning of fossil fuels, we are releasing carbon dioxide into the atmosphere at a rate that is likely even faster than the peak eruptions of these ancient volcanoes. We are, in a way, replicating the gas release phase of a lip, but in a fraction of the time. We are running the same experiment. We can see the early stages of the same effects. The planet is warming. The oceans are acidifying. Oxygen minimum zones in the ocean are expanding. The parallels are hard to ignore. The volcanoes of the past show us the planet's breaking points. They show us what happens when the chemistry of the atmosphere is altered too quickly for life to adapt. They are a record written in stone of how fragile our world can be. They demonstrate that the greatest threat to life on Earth doesn't always come from the vast emptiness of space. More often it comes from the planet itself. So, was it a volcano that wiped them out? For the dinosaurs, it was a co-conspirator, the villain that weakened the victim before the final blow landed. But for the countless species that perished in the Great Dying and in other extinctions, the answer is yes. It was the Earth's own inner fire, a slow, relentless, and suffocating eruption that turned a vibrant, living world into a wasteland. The greatest killers in our planet's history were not monsters with teeth and claws. They were cracks in the ground, quietly and patiently poisoning the sky.